Hi, in this video, I will talk about backends in Qiskit. In this video, we will see how we can use different quantum simulators and also how we can run a quantum circuit on a real quantum computing hardware through IBM Q service. To see what quantum simulators are available through Qiskit, you can print backend names. Here you see 4 available quantum simulators. The first one is the one that we already used. This is the QASM simulator, which allows multi-shot execution of quantum circuits. The second one is the state vector simulator. This simulator allows us to look into states without taking measurements, but we can only do this when we are doing single-shot executions. The other one is the unitary simulator, which allows us to get the matrix form of the circuits. This way, you can execute a circuit, then get the whole matrix form of the circuit. The last one is the pulse simulator. In the pulse simulator, you can control the pulses that control these qubits as you do in a laboratory experiment. For all these simulators, you can see detailed explanations in the Qiskit documentation. So let's start our first example with the state vector simulator. We start as usual by importing our quantum circuits and the necessary objects. This time, we are importing some visualization tool called +StatesD and also the state vector simulator. Here, we will see the results of a Bell state. To do this, we start our circuit with 2 qubits. As you see here, we don't have any classical register. This is because we won't take any measurements. We don't need to. Then we apply a Hadamard, then a CNOT gate to obtain the Bell state. After setting up our circuit, we call the state vector simulator and execute the circuit to see the states. This doesn't mean execute here doesn't mean measurement. This is to get the states, and then we can use plot state city to observe the density matrix of the states. Here we see 4 towers, which represents the Bell state. The plot on the left represents a real part of the density matrix, and the right one represents the imaginary. In the Bell state, we have only 0, 0 and 1, 1 states, and therefore we see a matrix that is composed from this, and it doesn't have any imaginary parts. So what we can do with this is to debug our quantum circuits better. Let's see what happens when we take a measurement. With the same circuit, we can get a measurement added here and plot the same result. This time, we see that we only have a single tower coming up, and which means that we got the result 0, 0, and it has the probability 1 since this is a one-shot measurement. Let's look at how we can use the IBM quantum circuit. To use the IBM quantum circuit, we need to first register to IBM Q service. You can create an account by going to here. Here you can log in and create your account. When you log into your account, on the right, you will see available backends. These are the current available quantum hardwares, and here you can see the listed jobs in the queues. And here you can also see how many qubits are available for each backend for each quantum computer. To use IBM Quantum Experience, you need to go right and go into My Account, then click this Copy Token button. Then we will go back to our Jupyter notebook, and you paste your token to here. Then uncomment this line and execute it to connect to IBM Q service using your account. Then you can print provider backends to see the available IBM Q hardware. Then we can check the status of the backends by printing backend status, and here you will see how many jobs are pending, which are operational, and check and select the one that you want to use. It is ideal to use the LispEasy, so we can import this object from Qiskit providers and always use the LispEasy device for our example. But we should be careful here. If we want to run a multiple qubit experiment, let's say 10 qubits experiment, we need to have a device with more than 10 qubits. So here, when we print this, I get IBM QSX, but this will be different every time you run it, depending on the load. So we can run our circuit in the IBM Q service pretty much the same. Here we have the same circuit. I'm importing time here to see how long it would take to get our result back from the IBM Q. Here I use the least busy device as our provider. Then I execute the circuit to see what this bell state measurement will look like. So when we look at our results, we see that we got 0, 0, and 1, 1 as the highest as we expect from a bell state measurement. However, we also got some 0, 1, and 1, 0 measurements, which we were not expecting. This is due to the errors in quantum computers. Currently, the quantum computers have high error rates. This prevents us from doing really practical applications. This is why we mostly use simulations in our examples. But still, we can do some experiments with the current quantum computers. When you try some examples on the quantum hardware, you will always get errors like this. There is a field called quantum error correction to reduce these errors, and scientists are currently working hard to reduce those errors so that we can use quantum computers as we do in theory.